Hello, my amazing Algebra Half students. This is Mrs. A, and I love math. Today, we're really getting close to the end of your textbook. 134 Edition 2, 121 Edition 3, and we're talking about forming solids and symmetry. Now, this is one of the sections that definitely has a lot of pictures in it, and so I'm going to be showing you some of these in your book. Okay, so here is the first part of the book here, and I just wanted to make sure that you could see it. It says visualizing solids that can be formed by folding patterns is interesting, and I can't draw that to where you can see it, so I just decided to show this to you in the book. It says, what is the volume of the geometric solid that is formed by folding the shape along the dotted line? So dimensions are in inches. So you can see here, let's see if I can make it a little bit bigger for you and still hold it on the screen here. There we go. That's a little clearer. Okay, so you can see that my side lengths are 5, 4, 3, 3, because you know this one's going to match this one when you fold it up. 4, 3, and then of course this one up here, I lost the top of this thing. There we go. Got the whole thing in there. So this one must be 4 also up here. And then this one here should be 3 because it matches this 3 when it folds up. So hopefully you can see how this flat figure is going to fold up to make this rectangular solid. And we have, once we fold it all up, this box. Okay, so this rectangular solid has a 3 height, a 4 width, and its length going back is 5. So the volume is length times width times height. So we would multiply 3 times 4 times 5 is 60 inches cubed. Since it's volume and since the dimensions are in inches, we will have volume in inches cubed. And all we do is multiply the length times the width times the height together. Okay, this second example says, what is the volume of the geometric figure formed by folding this shape along the dotted lines? Dimensions are in centimeters. Now, if we look at the shape, we can see that the top and the bottom of the shape are triangular. So this is going to wind up being a triangular, right triangular solid, which is a prism, isn't it? So this side's going to fold back and this side's going to come around, and these are going to be, the two triangles will be the top and the bottom. So can you see that when we fold that object all together, we will get this triangular solid, which has got a 3 and a 4 on the triangle top and bottom. Okay, and then over here, the distance going back is 5. So now we're going to have the volume of this figure. Now, if we sat this figure up on its side, it would be a right geometric solid, right? So it is it's cylindrical in its shape. So what I'm saying is we're going to pretend like this is a triangle because this is pretty close. This is my name tag. But if we pretended this was a triangle, in the book we're seeing it sit kind of like this. But if we turned it this way, then wouldn't it be a cylindrical shape? A cylindrical shape is all the same all the way up. And the volume of any cylindrical shape is area of the base times the height. And that's where we're going to find the volume of this figure by setting it not this way like it is in the book, but this way, so that we have the same shape all the way up, so that it's area of the base times the height. So that is where your book is getting this volume formula here. The area of the base, when we have set it up on its end like this, is the triangle. And the area of a triangle is 1/2 base times height. So we're going to find the area of the base, and then when it's sitting in this configuration, isn't this height equal to this length that's going out here? So instead of height, they're using the length because they're sitting it up on this base, and so the length was 5. So they're going to take 1/2 base times height, which is 1/2 3 times 4, 1/2 3 times 4 times the length 5, and we end up with 1/2 of 4 is 2 times 3 is 6 times 5 is 30 centimeters cubed. So let me zoom in on that a little bit so that you can see that configuration. So anytime we have something that is cylindrical in its shape, which means it's the same all the way from bottom to top, then when we sit it in that configuration, then it's just area of the base times the height. So it's going to sit on that triangle, and this 5 is going to be the height, and that's how we get that calculation. So now I wanted to show you their discussion of symmetry because their pictures, again, are much, much better than I could do for you. So up here at the top it says a figure is symmetric about a line if one side of the figure is a mirror image of the other side of the figure. This figure is symmetric about the dotted line. So now here, when we could fold a figure on the dotted line and the figure would actually meet itself on the other side. If I folded it on the dotted line, wouldn't these two sides lay on top of each other and be exactly the same? Therefore, we say the figure is symmetric about that dotted line. Okay, so here it says figures are symmetric about a line if the perpendicular distance from any point on the line to the figure is equal to the perpendicular distance from the same point to a corresponding point in the figure that is on the other side of the line. To demonstrate, we have picked 3 points on this dotted line. So basically what they're saying here to demonstrate this symmetry is that the distance between this point to this portion of the figure must be the same as the distance from this point, which is on the dotted line, to this part of the figure. So let me see if I can get that a little bit bigger for you. Okay, so again, on this one, this is the second point that they have drawn on the dotted line. The distance from the dot to the end of the figure, perpendicular to this center line. Perpendicular means right angles, right? That's a right angle right there. And then a right angle right on this side too, going straight down. This distance must be the same as this distance up here. And lastly, since this is also on this dotted line of symmetry, this distance here till it touches the figure again, and this distance here must be the same. In this next section, it says a figure can have more than one line of symmetry. The equilateral triangle has 3 lines of symmetry, and the square has 4 lines of symmetry. Okay, so we have equilateral triangle, and we have the square. All right, so the equilateral triangle could be symmetric about this. You see, this is a vertex, and the line that splits the triangle coming from the vertex, and then from here down to the other edge, and then from this vertex all the way across. And if we folded the triangle on any one of those lines, those dotted lines, then it would meet itself on the other side. Likewise, here we have a square, and it has 4 lines of symmetry. So I'm going to fold some shapes for you. The first shape we saw was an equilateral triangle. So I was able to make an equilateral triangle using my compass, and I'll show you that another time. But here we have an equilateral triangle, which means that all of the sides are the same length. Okay, so we saw in our figure that we could fold the triangle exactly on its vertex. Okay, so I'm going to fold it on its vertex, and I'm going to make sure it matches on the other side. And when I open it, you can see the line of symmetry. But I'm going to, with my pen here, just make a little dotted line, dashed line, to show where that line of symmetry was. Oh, it's so light you can't see it very well. Okay, and I did make a little dashed line on it there. Okay, so I need to make it a little darker, don't I? Okay, so then let's fold it in the other direction. So now we folded it here once, so now we're going to fold it on the other vertex here and try to get it right on the vertex, and then run it down the side, and then make a crease, and the crease will divide the triangle exactly in half, and I will make the little dashed line there, and I'll do it a little darker than I did the first time, and I'm going to make the other one a little darker too. So now we have 2 dashed lines of symmetry on our triangle, and now we're going to do the third one. Now we used this vertex, so this vertex is the one we have not used yet. So we're going to fold along. This is a fun project to do at home to demonstrate symmetry. So I folded it so that the corners meet along that third vertex. So now I'll draw the little dashed lines, and the lines intersect right in the center of this equilateral triangle, and you can see all 3 lines running through it. It folds exactly on 3 lines of symmetry. So our figure looks exactly like this. So now we're going to fold the square to look exactly like this. For my square, I have a sticky note. So here we're going to fold the sticky note in half this way until it meets itself, and I have a line of symmetry. So I will dash my line of symmetry like that. Okay, and then we're going to fold it the other way in half. Sticky notes are sticky on one side. And you can see I have another fold right there. I got a lot of light coming in here, but I have a lot of another fold, and the light, although I love the light, does make it harder to see this. Okay, so now can you see that I have split it in half this way, and I have split it in half this way? But I have 2 other directions. I'm going to come up here to the corner, which is a vertex, and I am going to fold it into a triangle. So I went from corner to corner this time, and when I open it up, I have another line of symmetry. And I've got one more that I can make. So I used this corner and this corner, and now I'm going to go and use this corner and fold it on the corner, matching the other two free corners, and I get another triangle, and the two sides are matching. So there is my fourth line of symmetry. Okay, so I'm going to make another dashed line there, and we have made a figure just like the one that is in our textbook. Right there. You see, we folded it in half and in half again, and then we folded it from corner to corner and corner to corner. So a square has 4 lines of symmetry. Okay, so now we're talking about symmetry about a point. This figure is symmetric about a point shown. Now, this, if we spin it around the point, won't it turn out to be the same? So if it is symmetric at a point, we can take this one and go 180 degrees this way, and the figure will lay back on itself. So I found 2 protractors that were exactly the same, and I taped them together, very similar to the figure you just saw. And I'm going to put a little dot of symmetry here. And I'm going to find what I think would be the point of symmetry. You see here that it's the same distance. This one is on the 5, and this one is on the center of this one also. So if I go exactly halfway in between here, then it would be at this point right here. And so I'm going to put a little dot on the spot that I think would be the point of symmetry on the figure. And now we're going to put the point of symmetry on the figure on top of the point of symmetry on the board. And so we're going to move this over here like this. So now we have this situation. So now what I'm going to do is I'm going to very carefully get it in the right spot. I'm going to trace the figure. So as you can see, I've traced the figure in green. Okay, so now I'm going to get a pencil or a pen, and I'm going to hold the symmetry spot down. So now I'm going to try to turn the figure with the eraser or the pencil. Not working very well. So let's just try to put my finger there and then spin it about its little point of symmetry, trying to keep it the same. Now, I am only spinning it 180 degrees. And in a perfect world, without any slide, it should wind up right back on the position that it was to start with. Okay, so now we're going to try it one more time since I've got my daughter here videoing for me. I'm going to put the pencil right here at that point of symmetry, and I'm going to spin. Notice the outline. I'm going to spin it 180 degrees, and it lies back on itself. It had a little bit of slide because the pencil is supposed to be a point, and it's not a point. But 180 degrees, it winds right back on itself, and that's what a point of symmetry should do. And this is the last little part of this section. Before we do our homework, it says a figure is symmetric about a point if for any line drawn through the point, it is the same distance in both directions to corresponding points in the figure. So basically they're saying, okay, here's the point of symmetry, and any line that I draw through that point is going to be the same distance from the point to this side as it is the point to that side. And that is a point of symmetry.